our research is mainly focused on develop and deploy a coastal science and engineering capability to empower science, energy, environment, and security. Okay, so the lower right map shows both view of the Screen campus. We have a total about 80 people with about maybe 20 to 25 people in the Seattle office, and I sit in the Seattle office. Okay. So this slide shows the estimate wave and ocean current and the tidal energy. And this number actually is from the DOE funded research for MHK resource assessment. So this map, I like the blue and the red color. It's artistic interpretation of the resource. But the table at the middle of the map shows the hotspot or the top early market locations. Okay, for example, in terms of a wave, the West Coast, especially Oregon, Washington, and the Northern California is the early market out hot areas for wave harvesting. In terms of tidal energy, Western Passage, Puget Sound, and Cook Inlet come up as the top 3 sites. So today I'm going to just go through some example, mainly cover those areas. For wave, actually I will cover pretty much the entire Pacific Ocean, which consists of the West Coast, Alaska, and Hawaii and the Pacific Islands. Okay. So I will start with the tidal current resource characterization and why modeling. Okay, well, of course, I've been doing numerical modeling since I graduate with my PhD, so it's really a fun job for me. I really like to do it, but it's really mainly the numerical model can provide a large spatial and temporal coverage. It's very efficient, right? Once the model is being calibrated and validated, it can produce a rich three-dimensional data set. And for the MHK, especially for wave and the tidal energy, they are very or highly predictable. So it is very suitable for to use numerical models for resource characterization and assessment. Okay. However, that doesn't mean measurements is not important. Actually, measurements are equally important because for any numerical models, without model validation, they really lack of the confidence in terms of application, right? So, and also for a specific site resource characterization, just a few, spot measurement that will provide a lot of value. So again, I just want to emphasize measurement is important, and I will show you later in terms of a model validation using extensive model field measurement. So for resource characterization for tidal energy, typically there are a number of approach, and very typically people first of all look at is velocity magnitude of a particular site, right? However, we know tidal energy, we should quantify this power, right? So power density is like I showed in here is the first, the formula. It's proportional to the cube of the velocity. So that is for one particular spot. It's give the unit of watts per square meter. However, if we want to look at the maximum potential or how much energy is available across a channel, then we need to apply to the cross-sectional area, right? We need to integrate the power densities across the channel. So you multiply, this is just a simplified a form to express the formula, just applied by multiplied the area of the cross section. This does not consider the back effect of tidal turbine. When you extract the energy out of the system, actually it also interacts with the ambient velocity, right? So it's a back effect. So it actually you cannot extract all of the energy because you're going to slow down the velocity field. So in order to accurately to estimate the extractable energy, one common approach is to use a numerical model, and then we introduce a momentum sink in the momentum equation. Okay, and it's a similar form, and but it's with specification of the tidal turbine. So here the AS is the swept area of the tidal turbine. So it's a function of turbine diameter and also the thrust coefficient, which represent the efficiency of the tidal turbine. So the three sites I mentioned earlier, okay, Cook Inlet, the Western Passage, and Puget Sound is shown in the map here. And it's very complex, the system of all of those three, and they are also quite different. Okay, so I'm going to just mainly focus on Puget Sound because we have been working a lot in Puget Sound, and we have a lot of data to demonstrate why it is one of the top sites. And it's very complicated. So I like to use the Puget Sound as a major example, but I will also touch base a little bit on the Cook Inlet and Western Passage. So like I said, the Puget Sound is very complex actually with a strong tidal current, okay? And this map shows the model bathymetry portion of the model domain, okay? So the model we use to simulate the tidal current in this study is the finite volume community ocean model, FVCOM. It's covered the entire Celtic Sea, which include the Strait of Juan de Fuca, Georgia Strait, San Juan Island, and the Puget Sound. Of course, the Puget Sound, then it can be further divided into sub basins, such as South Puget Sound and the main basin, Cook Inlet, not Cook Inlet, Hood Canal, and the Whidbey Basin. Okay. The model resolution in the tidal channel is about 50 meters, which is very fine, be considered the large model domain. And we have about 20 vertical sigma layers. We also have a model with 30 vertical layers, but we find that they are more or less similar in terms of model result. Okay, and the model grid has about 1.5 million elements. Okay, and we validate the model with 12 water levels, tidal gauge station, and also 135 ADCV stations. And those stations actually, those measurement is collected by NOAA back 3 to 5 years ago. Okay. This is a model and the data comparison of water level. Okay, this is the total water level, but you can see the model can successfully reproduce the tidal propagation from the Pacific Ocean through Strait of Juan de Fuca, and then propagate north to the Strait of Georgia and the south to the Puget Sound. I want to point out a couple of things here. So on the top left panel, right, that's the Port Angeles station. It's still mainly dominated by, the diurnal tide. And when the tide propagated down to Tacoma or South Puget Sound, you can see the semi-diurnal component being amplified, and you can see the inequality of, the diurnal inequality in the tidal signal, and also amplitude is much bigger than those in the Port Angeles. Okay, and all those of 12 stations, the model actually have excellent match in all of those characteristics. And We also compare the model, predict the three-dimensional current at all the 135 station. Okay, I actually want to point out that the map here. So these are all the triangles represented ADCP stations collected by NOAA and from 2015 to 2017. Okay, each station has about 3 months of a record. Okay, so a lot of data, and we simulate for those period and compare to the model result with the data in the three-dimensional domain. So this is just a 3 station for example. Okay, so we compare not just the time series and the scatter plot. The scatter plot actually gives you how the model in general in terms of the direction, how well the model predicted in terms of the direction. But also we compare to the vertical profile. Okay, vertical profile is a little bit tricky because of you have so many vertical profiles. So we are in the process to calculate how many percentile in terms of the model compared to the model predicted and observe the value. The other important parameter, which also recommended by the IEC technical specification, is the percentage of probability distribution. Okay, for example, in Rosario Strait, the velocity the current speed distribution is more on the lower end. Okay, you can see the percentage. However, in the Admiralty Inlet, it's much broader, right? It's up to about 2 meters per second. So you still have a quite large range of velocity distribution. However, in the Agate Passage, high percentage actually is around 1 meter per second velocity magnitude. Okay, so if you look at the vertical profile, you can see more lines actually around the 1 meter. So velocity actually turn around very quickly and reach to about 1 meter to around 1 meter per second range and stay there for more duration of the time. Okay, so these are very important characteristics. So we are not just in terms of tidal energy, we are not just look at the magnitude, right? And the distribution of the currents is important in terms of design, device design, and the site selection. I mentioned earlier, there's like 3 typical type of approach when we quantify the tidal energy. Okay, so a simple way to look at, okay, where's the has the highest speed, right? And the deception path, actually, I want to use this example why it's important to consider the cross-section power. Okay, deception path, it's well known, right? Has the highest speed in Puget Sound. Even just a mean velocity, it's about 2 meters per second. Okay, so if we rank by the mean velocity, and deception path comes up as the top one, right? However, if we apply to the cross section, okay, to calculate the flux, then we get the power, then the order immediately change, and you can see the Admiralty Inlet and the Tacoma Narrow become the top one, top, and also the second largest in terms of potential power. Okay. So next, I just want to quickly demonstrate what we can use a turbine a module in the numerical model to simulate energy extraction. So Tacoma Narrow, like I mentioned earlier, is one of the top site in Puget Sound for tidal energy extraction. Okay, so we actually refined the model grid to down to about 30 meters. Okay, actually, I believe some area actually is even smaller than that. And then we place hypothetical tidal farm. Okay, it's completely hypothetical. So with 20, 50, and 100 turbines in Tacoma Narrow. And the tidal turbine diameter is 10 meter, and the rotor, okay, there's a typo here, it's a hub height, it's 10 meter from the seabed, okay? And so this is 3-panel lower panel shows the extracted tidal energy, okay? And it, you can see in the lower right, this is a comparison between spring tide and the nip tide. So Puget Sound is a strong spring and nip tidal cycle, okay? And you can see it's almost an order of a magnitude the difference in terms of spring and nip, okay? So those are the important consideration when we look at the tidal energy. We cannot always just look at the maximum, right? So if you look at the daily average, that's this lower left figure, which shows, you know, then it's much smaller, right? So because you look at the daily average, it's not like, you know, hourly tidal cycle. So then even with the 100 turbine, you actually, the extractable power is about 12, the maximum, okay, 12 megawatts. So remember earlier we showed, I mean, in the Tacoma Narrow, actually, those are, again, number, it's a very rough estimate, okay, it's a 60 megawatts. So, but if you do a monthly average, it's much smaller because, you know, during nip tide, and actually it's only maybe even less than 2 megawatts. We also look at the environmental impacts. We always, you know, face this environmental concern, right, when we place anything in the water. So this slide shows with and without the turbine in place and how the velocity compare, right? So the blue line in the vertical is the vertical profile of velocity without the tidal turbine, and the red line is with the tidal turbine, and you can see the deficit, okay, which is a dash black line. So we still see, you know, about the 20% deficit right at the turbine place. However, system-wise, we really don't see anything in terms of flow field, okay, effects on the ambient flow field. But if we look at the bed shear stress and the velocity, and you can see also, you know, the deficit even for a 20 turbine farm. Okay, so at the local scale, it is still important in terms of environmental concern. Okay. Now I would like to quickly go through the Eastern Passage, Western Passage in Maine. So we developed the model with some very, very high resolution, about 20 meter in the Western Passage. And the model domain cover partial of the Gulf of Maine and the entire Bay of Fundy, okay? And this is, again, it's a model and the data comparison. On the left is the water level comparison. And you can see, compared to the Puget Sound here, we still see spring and the nip tidal cycle, but it's nice semi-diurnal dominant system, right? You don't really see diurnal in the quality in the tidal signal. Okay, you basically see pretty much equal two peak and two peak flood and ebb in one tidal cycle in one day. And on the lower right, it's a comparison of vertical profile of velocity magnitude, okay? And you can see the model comparison, it's model and the data comparison actually is quite satisfactory. And this is at the location of Western Passage, and the data was collected by NREL. There's a very limited data actually in the Western Passage, okay? I would like to show you how we can actually use a three-dimensional data to help us to select the site, right? So on the left is horizontal 2D depth average velocity. I think it's the first surface velocity. flood current. Okay, so based on that, we can identify some hot high current area, and if we look at the cross section power density, and we can see a lot of variation. Okay, so this is important. And if you actually look at the bottom right panel, it's quite nice actually for in terms of the horizontal distribution of power density and also the area. However, this is relatively shallow. I think that's one of the reason it hasn't been really explored in that particular location, but it's also actually it belongs to Canada. So for that cross section 4. Okay. So, but when we generated this result, actually, there's quite a lot of interest. I mean, or question asked about, okay, is this channel has been looked at it? So, I would like to share one slide on the Cook Inlet, okay, modeling. We did some preliminary. The model actually is already developed with very high resolution, with a focus in the eastern and the west Foreland area. That is the area with the highest tidal current or power density. However, the model right now we currently develop do not consider CIs. Okay, and we recently have another project that look at the CIs in Alaska in general, in particularly at the Cook Inlet. Actually, there are a lot of CIs in from December to until February or even March. Okay, and the drifting down from the upstream. Sediment is another issue because of a large river discharge, and ice melt also carry a lot of sediment downstream. And the wave and the current in direction in the lower bay or lower inlet also is important. So I will show you in the wave Handcast and why in this area it's wave and the current in direction is important. So I'm going to switch gear to wave Handcast. Let me look at the time. Okay. So currently, we have a project funded by DOE. It's a multi-level project, and the PNNL is leading the Handcast, and in collaboration with Sandia National Labs. Okay. We use a high resolution unstructured grid swarm, and with a global nested wave watches 3 model, and we run all the model in-house within PNNL. And when I mention a high resolution, it means 150 to 300 meter in the nearshore region. Okay, it's covered the entire EEZ, which is about 200 nautical miles offshore. Okay, and the lower, the right panel with all those shaded area represent the U.S. EEZ regions. Okay, and the PNNL covered the entire Pacific Ocean, and Sandia covered the Atlantic Ocean coast. Okay, which consists the East Coast, the Gulf of Mexico, and the Puerto Rico. One thing I would like to mention is most of the NOVA also has Handcast, okay, and also real-time forecast of the entire region. However, their model is at the 4-minute arc-minute resolution, which is about equivalent to several kilometers. And also the spectrum and the partition outputs are not available, and that is very important. So in our model output, we do output the spectrum and the partition, okay, in the nearshore region. This is just again an example about the model resolution in West Coast, Alaska, and Hawaii. It's very, very fine grid. Okay, so for in Hawaii, it's a several millions elements. Okay, for the entire region. So it's very computational intensive actually. So luckily we have a high performance computer within DOE. So we were able to perform those simulations. Just a quick comparison. Our Handcast focus on nearshore means within 10 to 20 kilometer offshore. Okay, in the nearshore, along the shoreline, we definitely have 200 meters resolution or even finer. Here's a comparison on the top two panel, the NOVA Handcast, okay, which has a resolution of 4 arc minutes, and the bottom two panel is from our Swan simulation. And then if you look at the left column, it's West Coast, actually is in Southern California. And you can see actually the NOVA Handcast, because of the resolution, limitation of resolution, we won't be able to really have accurate simulation for very near shore. However, with the Swan simulation, you can see actually it can well predict the hot spot and also the two cold spot. Okay, so now if we look at the right column, that is in Alaska and the lower Cook Inlet. So in the Noah's model, because of the resolution, it actually does not further extended further into the Cook Inlet. Okay, and that's also why it would not allow more wave propagating into the Cook Inlet, right? If you look at the bottom right, that's our simulation with the Swan models. And we also closely follow the International Electrotechnical Commission's standard. Okay, we compare the model simulation with data derived 6 IEC resource parameters. So this is just one example, a model and the data comparison at the buoy 46211 in the, on the Washington coast. And we did this for all the available buoy, okay, as long as the buoy data is available and within our period. So, and I mentioned earlier, we also output the spectrum and the partition data, right? So we done not just compare the time series, but also look at the spectrum distribution. So on the left side, you can see this is again in the California coast. I use this, it's because if you look at in the summer, the two top two comparison, you can see in the summer, you actually have element, I mean, a component wave energy propagated from the south, okay, southwest. That is the swell actually from the Southern Ocean and the Southern Pacific Ocean. So, and the model actually was able to reproduce that. That's we show in the data, okay. And of course, we also look at the bivariant histogram, okay, which look at the percentage distribution of a wave climate as a function of significant wave height and energy period. Okay, so you can see the model actually and compare very well with the data. And these figures actually is important again for selected type of device for any particular site. Okay. This is a similar figure actually I showed earlier. Again, this is, but it's at a different site. With the resolution we have in the model, it can well identify some of the hot and the cold spot. Okay, this two location, it's just about the 10 kilometer apart. Okay, and you can see in the hot spot, it has much higher wave power, and we can see the direction. Okay, it's from west and the west northwest. But in the cold spot, it's very just straight from the west. Okay, and the wave power, it's much smaller. So for the partition output, the useful of a partition output is we can use to identify how the multi-module C state, okay, for example, wind C and the swells, okay. So this is the 4 locations, okay. The top 4 represent the winter season, and the lower 4 panel shows the summer season. You can see actually in Washington and Northern California, actually, I don't have a station in Oregon, but it's also represented in Oregon. In the Northern California and Oregon, it's quite similar. You can see the wind sea actually is quite spread, okay, from the southwest and also from the northwest. And very strong westerly propagated swells. But in the Southern California, in winter, we barely really see much swell, okay? However, in the summer, you can see very distinct swell actually coming from the southwest, okay? This is what I showed earlier in the 2D spectrum. You can see actually wave from the Southern Ocean propagate to the, reach to the California, Southern California. We also look at the seasonal variation. Okay, that's again for those 4 locations. Okay, in the Washington and Oregon coast, there are strong seasonal variation. Okay, so in the winter you have large power, but in the summer it's much calm. However, in the Southern California, the variation, the seasonal variation is not as strong. Okay, because we simulate 32 years wave climate, we will be able to look at a long-term variability. Okay, so in this plot, it shows the anomaly by remove the 5 years average mean. Okay, so then we can see actually there's some peak. Those peak actually the variation corresponding to the ONI index. Okay, those are corresponding to 3 major El Nino events. Okay, so it indicates a long-term Handcast is important to quantify the wave resource, because if you look at the anomaly, can as high as 15%. Okay, if you miss those peaks, actually will induce high uncertainty in the wave resource assessment. So for Alaska and the Arctic, I'm not going to go to the detail, but the analysis is similar. But this is just 32 years mean of 6 IEC parameters. Okay, we are in the process of write up the paper for the Alaska region, and we produce this type of a map for all the region actually, right from West Coast, Alaska, Hawaii, and the Pacific Island, the East Coast, and Gulf of Mexico too. So. Recently, there's been increased interest in powering blue economy, especially for remote islands. Okay, so even though our study or our funded project is not for the powering blue economy, but because we produce a very high resolution wave data, this data actually immediately become useful for the remote computing or islands. Okay, so this is just an example of look at the Maui around the island, and you can see because the wind around the island, Okay, so you're facing up out in the leeway of the wind is very different. So if you look at the wave energy distribution, this is the power roles of distribution. You can see it's very different. So in the northeast direction, you can see the wave can propagate from the northwest, but also from the east. Okay. However, on the other side, you can only because of a blocking of the wind, and you can only see the um, northeast direction wave. Okay. Yeah, this is just an example. On the lower uh, left, that is the average power for all the major islands. We just integrate around 5 kilometers from the shore. Okay, so it's average power for each of the islands. And lastly, the environmental condition is important for wave energy converter deployment. Okay, so what we call the environmental controls. These controls are produced to assess the extreme events. For example, corresponding to 100 years of return period. Okay, so if we look at from the west coast to Alaska, Western Aleutian Islands, we can see the wave height actually for the extreme 100-year return period start to increase. Okay, so so this is the map. I mean, or the plot of the envelope. However, if you look at the Hawaii, wave height is much smaller, and so this. However, the wave period corresponding to the 100-year return period, it's vary quite a lot. Okay, so just this is just an example how the data can be useful or can be used to support WEC deployment. Okay, that's all in terms of my presentation on the wave and the tidal energy resource characterization. I just want to use this slide to share, the opportunity in PNNL, and we really want to, build a strong PNNL and the PMEC partnership. Okay, so I believe I share the distinguished graduate researcher program with some of you already. Um, I understand that this seminar is mainly targeted on the graduate student, but I would still like to share the SULI program at the PNNL is an important program. It's completely funded by DOE, and it's a very prestigious program. They support you for anyone who is interested in related to energy or any work in the national lab. Okay, that's mainly for undergraduate students. And it's run actually throughout the year, but most of the students actually participate during the summer. And of course, we continue, constantly, have internship and also postmaster and postdoc positions within PNNL. And those positions actually have a potential to converting to a regular staff. And just a few example of a research area. It's not just marine renewable energy, but also other areas too. Okay, I think that's all my slides, and thank you. I hope I have some time for questions. Yeah.
I love the virtual class. Thank you so much, Zhaoqing. And we'll distribute those links that he shared in the previous slide over the email list for people to check out, and also post these slides somewhere where everyone can access them. And we also did record today's talk, so that will be available as well. does anyone have any questions? Please feel free to speak up.
Hi, this is Pedro Lomonaco from Oregon State. Thank you for your presentation. Was very, very interesting. How accessible is the information, the post-processing information that you presented? For example, Handcast and long-term prediction of wave conditions, for example, along the coast of Oregon or something like that. How can we get that information, that post-processing information?
Very, very good question. Actually, yeah, I was actually running out of time, and I was hesitant. I mean, was, you know, coming back and forth whether I should include one slide for that. Actually, as I mentioned, this is a multi-level effort. The NREL is taking the lead to post all this data live through Amazon web server. So West Coast now actually is already live. I mean, online. Okay. I'm going to include the one slide in my slide deck and then share with you. I mean, Paul, so that you know people, if interested, they look at it there. And Alaska is in the process to up online. Okay, so you can just go and click. I haven't try it yet, but I know the last couple of weeks we have some internal meeting and share those links. So I will definitely include one slide for that.
Thank you very much.
And that also include the tidal side. Okay, so both tidal and the wave. So.
Sorry, just an additional question. Do you have information on water levels near the coast? Something that could be include, for example, storm surge or tidal level, so vertical tide?
Tidal level, no, because well, tidal level it's very easy to find, right? So if you Google, you know, NOAA tide and currents, you pretty much have those. But on the tidal Handcast, we do have, you know, collected tidal elevation, and that should be available. But not
more,
storm surge.
No storm surge.
Yeah,
exactly.
not storm surge.
Meteorological tide or anything like that. That's something. Okay.
Yeah.
Okay.
We actually do a lot of storm surge simulation. So yeah, that's a good question. We are actually in the process of developing our own group website, and I would like to put those actually storm surge data actually online too. So good question. Actually, that's, you know, a good
Thank
feedback to push the management. Okay, put the web online.
Great.
So.
Can I jump in with a question? I'm not sure. This is Bryson Robertson at OSU. Great presentation.
Hi, Bryson.
Yeah, with building on Pedro's comment there, I know NREL spent a lot of time figuring out how to put the stuff online. We actually had an undergrad student just recently test out the system and see how easy it was as someone completely unfamiliar with the project.
Yes.
And he's just putting together some slides right now, and then he was gonna give a little presentation to some OSU students around how to do it. But we could expand that to a number of other people, and Zhaoqing, it'd be great if you were able to join us for that.
Yeah, I would be interested to know. Actually, this morning we just had another meeting, you know, about that. So, yeah, basically you guys will serve us like a beta testing.
Exactly. We're just
yeah.
trying to figure out where the bugs are before it goes very public, but it seems like it's actually fairly accessible. So we'll follow up through the channels around when and where and how.
Okay, perfect.
Very cool. Thank you so much for that talk today. Found it very interesting. I have a couple questions, or a question about some of the turbine simulation work that you were doing. Mm-hmm. Did you model, now I may have missed it, but I believe the data set was on a 20 turbine model for the impact on the water column. Did you model the 50 and the 100 as well and see similar results?
Yeah. we did, but this one, right?
Yeah.
The result actually is similar because it really depends on how far apart you place in terms of the turbine, right?
Mm-hmm.
So that we didn't plot this together, but they are more or less they are similar. So
Gotcha. Thank you.
yeah, we did not really increase the density of the turbine. We just laid it up a little bit more. I think I showed it here.
Okay. Yeah.
So you have a more row across the channel, I think. Yeah. This is a little bit denser. So the 100 one, I think it's 100 probably we'll see, but it's yeah. We didn't plot that. We try to emphasize even the small number of turbine. It causes enough deficit, velocity deficit. So
very cool. Thank you again.
While you're on the slide, I had a question about actually the previous one. Colin Wilson from UW. I'm curious about the economics of this sort of project, because like the total amount of power that you're getting out of 50 turbines is not all that much. How does that look in terms of cost of a project, and is it just that what you are modeling is maybe not the target size of a turbine? Maybe we need to be picking for bigger turbines or something. Like what would allow us to make this really feasible? Because, for example, I looked up like the Colstrip coal power plant is like 1,500 megawatts, and now we're getting like 20 megawatts or something like this. So we're not taking a huge dent out of bad energy sources.
Right. Very true. I'm probably not the best person to answer that question, but it is very. I think it's also part of the reason why this side, get kind of a stop, right? But yes, however, on the other hand, I want to demonstrate using the numerical model is, yes, if we at the stage you want to look at the economic benefit and versus the cost, right? And this tool will allow you to play around with, okay, what is the turbine size and how the impact would be. Okay.
Yeah. So basically, we have a tool here that can be used by other people downstream to figure out where the best place is.
Yeah, and so far we don't even have a turbine farm actually as a test site in US, right? And I mentioned at the very beginning, yes, I like model is great, but we need the data, right? We need the measurement data to validate, is this true? Is this exactly how much or not exactly? We actually, at least the model predict the reasonable powerful extraction with the collector number of the turbine in place, right? This we haven't really even seen in the world. This that type of data and the model comparison. So this indeed is still a challenge, but yeah, I think the point again is like I mentioned before, we have a tool, at least we can explore the alternatives and have some comparison.
Thanks.
Colin, I
sorry.
sorry. Well, why don't you go ahead and I'll say that.
Okay, I had a quick question about the Cook Inlet in Alaska. I'm a grad student at UAF. So you mentioned that fragilised or sea ice was a big issue and that there was a lot of sediment. Do you have any way of predicting like where the best, like the risk of that would be, or like a good location to avoid some of those issues?
Yeah, We have currently we have a seedling project funded by DOE. Seedling means it's not a full project, but you know, some concept development. Okay, so what we really plan to do is to utilize satellite data. Okay, to identify the percentage of coverage of sea ice in the margin, especially in the upper bay, and then we simulate the drifting, floating sea ice, and to quantify the risk. I mean, where it's the location has the highest probability being hit by sea ice, for example. So, yeah, it is a challenge, and also, of course, that you know also maybe in terms of the technology side, they will try to develop a turbine or any other ocean observing system that can more sustainable under that kind of extreme condition or sea ice condition. Yeah, we are doing. I mean, have researching heading that direction. Yeah.
Gotcha. Thanks.
Sure.
I'll just jump back in. Colin, I liked your question, and I think it might be a good idea for us to schedule a seminar to discuss that further. I know just yesterday there was a meeting in Brian Pelagi's lab to discuss the Department of Energy's project to forecast the costs of different forms of renewables. And so it might be a good idea if I can schedule someone maybe from the DOE to come and talk about their current forecasts for the cost of energy and what a renewable portfolio could look like in the next 10 or 20 years, and how these technologies fit in. So thanks for asking, and I think I'll see what I can do for that.
Is the schedule for all the presenters this quarter set, or would that be like next quarter or something?
I think we still have a couple of open slots left this quarter, so there's some flexibility. But it is mostly filled up for the quarter, and I haven't started scheduling at all for the next quarter. So if anyone, I'll take this opportunity to say, if anyone has any ideas for speakers and would like to share or invite someone to speak at the seminar, please just reach out. Are there any other questions for Zhaoqing? Okay, I think we'll wrap it up there. Once again, let's thank our speaker with our virtual collapse.
Thank you. My pleasure.
Thank you so much, everybody.
All right. Bye.
Bye. I don't know how to stop recording.